Welcome to the fuel analysis concept of chemical process utilities. Now, before we go into the detail of the different aspect of fuel analysis, which partially we have discussed in the previous lecture, let us have a look about that what we covered previously. Now, previously we have covered the various thermodynamic aspect of power generation and refrigeration, in which we have discussed about the various concepts of different cycles, vapor power cycles, Carnot cycle, Rankine cycle, etc. Now, in this particular lecture, we are going to cover about the proximate and ultimate analysis. Apart from this, we will discuss about the concept of heating value. Now, before we go into the detail, as we know that where there are various chemical processes, they require the external heating for conducting a specific work. Now, whenever there is a requirement of external heating, we have to look into several different parameters. The one parameter or one aspect is the fuel. As we discussed in the previous lecture, there is a variety of fuels available as on date, but based on our requirement, based on other issues like environment, calorific value, etc., n number of choices available. So, in other words, we can say the variety of fuels are available to produce heat. That is the most generic term. Among them, the cheapest and easiest available fuel need to be used. The reason is that whenever we are discussing any process, or our ultimate aspect is to have a useful product from the raw material. In that case, if we are overlooking such kind of a concept like cheapest or easily available fuel, in that case our product cost will be on the higher side. So, we have to look into this particular aspect. Now, second aspect is the selection of fuel. Now, this usually depends on the type of use. Now, if contamination is the issue, then the high quality of fuel must be used. Like say the cheap quality fuel having the high contamination may be available at very low cost, but ultimately whenever we go for process which is attributed to the environmental issues, calorific value, efficiency of the system, then definitely the cost play a very vital role. So, we have to optimize the thing. So, based on this thing, we need to choose the fuel. Now, each fuel has its own advantage and limitation. Among them, the most referring factor is the amount of energy producing on burning of a unit mass of fuel. That is called the calorific value, and sometimes it is referred as joule per kilogram. Now, this is the foremost requirement as far as the engineering perspective is in question, because ultimately we have to supply the heat to the target. Now, other factors this include the amount of ash, pollutants, because ultimately environment issues, when we talk about the energy, simultaneously we cannot overlook the importance of environment. So, pollutants, volatile matters, other impurities, moisture, etc. All these things are need to be addressed when we are going for the choice of fuel. Now, to obtain these information, basically ash, calorific value, etc., there are two basic analyses need to be carried out. One is the proximate analysis, another one is the ultimate analysis. Now, let us have a look about the proximate analysis. Now, the proximate analysis of fuel, this determines that how much percentage of material is in the gaseous form during burning. That is, it reflects the quantity of volatile matter. The percentage of material in solid state, that is fixed carbon, the percentage of moisture in a fuel, the percentage of inorganic waste material, that is called ash. Now, they are determined by means of gravimetric tests, both direct and indirect, that allows their calculation. Now, higher volatile matter content, this can lead to increased gaseous product formation, and these gaseous products usually have a very low calorific value. So, a quality of fuel must be addressed. Now, usually a quality of fuel have higher number of fixed carbon content. This sometimes lead to higher charcoal formation used in industrial heating application. So, this thing is having advantage or disadvantage both the ways. Now, let us have a brief discussion about the proximate analysis. Now, usually when we go for determination of moisture content, usually it reflects in terms of percentage. So, first we must know that how we can measure this one. So, for this we require a crucible, and at the start, at the outset, you need to weigh the dry crucible like this. This is the some of the shape of the crucible. So, you need to weigh the dry crucible, put 1 gram of solid fuel into the crucible, and you need to spread it uniformly so that the layers and other things or stagnant zone cannot form. Again, weigh the crucible with the sample to obtain the exact weight. So, heat the sample in a microwave oven for say 1 hour, about 105 to 110 degrees Celsius, or any oven. Now, carefully cool the sample in a desiccator to avoid any contamination of moisture, because the atmospheric moisture may again re-enter into the sample, and whatever results you get, it may be erroneous. Now, then weigh the crucible. Then through this mathematical equation, you can find out that what is the moisture content, that is moisture content in percentage is equal to the loss in weight of the sample divided by the initial weight of fuel or sample multiplied by the 100. So, by this way you can calculate the moisture content. Simply, when we talk about the volatile matter, now you can place the same sample with a lid in a preheated muffle furnace at around 900 degrees Celsius for 7 minutes. Cool it in an open air for a minute and then place it in a desiccator. Then weigh the crucible with lid to determine the mass loss. Now, again there is a mathematical relationship through which you can calculate the volatile matter, which is again in percentage, that is the loss in weight of the sample divided by the initial weight of fuel, again multiplied by 100. So, by this way you can calculate the volatile matter. Then come to the ash content. Again you require the similar crucible. Again this should be placed in a muffle furnace without lid for half an hour, and you have to maintain the temperature between 500 to 750 degrees Celsius. You need to allow it to cool in open air for some time and then put it in a desiccator for cooling. Perform the again weighing operation for the crucible to determine the weight loss of the sample. Now, ash content again you can calculate through this mathematical relationship, that is the loss in weight of the sample divided by the initial weight of the fuel multiplied by the 100. It will give you the ash content in percentage. So, as far as we need to determine the fixed carbon percent, so there is a simple mathematical relationship to assess that what is the fixed carbon percentage in the sample, that is 100 minus percentage of the moisture integral part, then percentage of the volatile matter plus percentage of the ash content. So, by this way you can find out that how much percentage of fixed carbon present in the sample in question. Now, there are various standards as applicable by the ASTM, American Society for Testing of Materials, they put forward with a certain procedures or certain methods or certain standards for the proximate analysis. Like for moisture, the ASTM standard is D317311. That affecting parameters are storage durability, dry matter loss, heat loss, self-ignition, plant design. Similarly, volatile matter, ASTM D3175, it reflects the thermal decomposition behavior of the sample in question. Then ash, ASTM 317412, the affecting parameters are dust emission, ash manipulation, ash disposal, combustion technology, etc. And the fixed carbon, the prevailing ASTM standard is D317207A. Now come to the ultimate analysis. Usually we know that coal or any other biomass, it is very applicable for the biomass. So, coal or any biomass is composed primarily of carbon along with other elements like hydrogen, oxygen, nitrogen, sulfur. Now, it is quite essential to determine these elements before using the fuel for its effective combustion as well as for the utility design. Now, why I am talking about this utility design or effective combustion? Because whenever we are using its fuel, all these things may either hinder or may create a problem, because sometimes sulfur is present, then definitely it may corrode the system, or it may impart the hydrogen sulfide or any off gas which may create an environmental issue. Similarly, other nitrogen, oxygen, etc. like nitrogen, it will not impart any kind of calorific value in the system. So, before taking or before designing our utility system, we should know that what is the nature of the fuel. Now, ultimate analysis, sometimes it carries the information, relevant information pertaining to the elemental analysis, or sometimes it is referred as elemental analysis. This helps to determine the net amount of oxygen required for the combustion of a specific amount of the fuel. See, whenever we perform the combustion reaction, then definitely, because we need to know that how much quantity of oxygen is required. So, unless otherwise we do not have any clue about the combustible material present in that particular sample, we do not have any information, or we do not have any knowledge about the oxygen requirement in this case. So, therefore, this particular information is quite essential for assessing the exact requirement of oxygen. So, the determination of carbon, nitrogen, sulfur, this helps to control the pollution associated from their oxides, as I discussed, because this may pose the serious environmental problem. Now, let us have a discussion about the procedure through which we can carry out the ultimate analysis. So, first have a look about the carbon and hydrogen. You must have a specified amount or a specific amount of sample, maybe 2 to 2.5 gram of sample. Usually it is placed inside the combustion chamber, which is here in the figure. Now, the weight of the sample is to be taken very precisely, because ultimately it will give you a proper information. Then the combustion takes place in this closed tube where enough oxygen is supplied continuously for the combustion purpose. So, you see that here we are supplying the pure oxygen from here, and the carbon and hydrogen present in the sample, they invariably will convert into carbon dioxide and water or H2O. The oxygen gas will also work as a carrier for these gases to move outside the chamber. So, you are having the sample ports over here. Now, CO pellets, this will catalyze the reaction and allow the complete combustion of the carbon traces, and partially burn the CO gas. So, it will help for the complete conversion of hydrogen to water or H2O. Now, anhydrous CaCl2 and KOH solution, they absorb the H2O and CO2 respectively. So, by this way you can assess, because you are you have already have a pre-knowledge about these solutions. So, you can easily carry out that how much of carbon and hydrogen they are present. Now, the change in mass of these absorbers, these are the absorbers, they are monitored separately. So, whatever difference in occurred, it gives the amount of H2O and CO2 produced during the combustion process. So, you can take the cognizance of these two reactions, that is C plus O2 CO2 and H2 plus half O2 H2O. So, you can take the cognizance of this. So, with these reactions you can calculate. Through these mathematical relationship, you can find out that how much percentage of carbon is present in the sample by this mathematical relationship, that is the increase in the weight of KOH tube multiplied by 12, that is molecular weight of carbon multiplied by 100 divided by the weight of coal sample taken into 44. 44 is the molecular weight of CO2. Similarly, if we need to find out the percentage of hydrogen present in the sample, easily we can calculate the increase in the weight of CaCl2 tube multiplied by 2, 2 is the molecular weight of hydrogen multiplied by 100 divided by the weight of coal sample taken multiplied by 18, that is the molecular weight of H2O. Now, then next is how we can determine the nitrogen percentage. So, the determination of nitrogen is being carried out by the Zeldal's method. Now, the many organic compounds, when they heated with concentrated H2SO4 in presence of CuSO4 and K2SO4, the nitrogen get converted into NH4 whole twice SO4. Now, this ammonium sulphate obtained is then decomposed with the caustic soda or caustic potash, resulting in ammonia evolution. Now, this ammonia is then passed into the H2SO4 of known quantity and strength. So, the remaining unreacted H2SO4 is then titrated against the sodium hydroxide solution of known strength. So, by this way you can calculate or you can find out the percentage of nitrogen present in the sample. Now, this is a simple mathematical formula, that is the percentage of nitrogen 1.4 into normality of the acid multiplied by the volume of the acid used with ammonia divided by the weight of organic compound, and this is the Zeldal setup. It is a very common and it is frequently used in the determination of nitrogen content. Now, another method for determination of ultimate analysis under this nitrogen determination, that is by the Dumas method. Now, this again Dumas method is the nitrogenous compound when heated with the cupric oxide in carbon dioxide atmosphere, this converts into the free nitrogen, and the simplified formula is that CxHyNZ plus 2x plus y by 2 CuO, that is equal to x CO2 plus y by 2 H2O plus z by 2 N2 plus 2x y by 2 Cu. Now, this is the typical diagram of Dumas method. Here there is a cupric oxide gauge, and this cupric oxide and organic compound, they are placed over here with the under the edges of coarse cupric oxide and the reduced copper gauge, and continuous supply of CO2 enters into this one, and this is the typical anatomy of the furnace. And this it is subjected to this mercury chamber where nitrogen is get collected with the help of displacement of KOH solution, and by this way you can find out the volume of nitrogen. Now traces of oxide of nitrogen, it can also be produced, which are reduced to the elemental nitrogen by passing over the heated copper spiral like this here. Now to begin, the nitrometer strap is left open, and to discharge the air in the combustion tubes, and CO2 is fed through it. So when potash solution fails to reach the top and is fully absorbed by rising gas bubbles, it indicates that only CO2 is arriving and that all air has been evacuated from the combustion tube. After that, the nitrometer is filled with the potash solution by lowering the reservoir and closing the trap. After this, we can heat the furnace and the temperature is raised progressively. The nitrogen catches the nitrogen that has been released from the chemical. Now, when the combustion is completed, a high stream of CO2 is pumped through the device to remove any remaining nitrogen, and that is called the flushing of nitrogen. So, you can flush it out so that any remaining nitrogen can be collected and measured. So, after adjusting the reservoir such that the solution in it and the graduated tube are the same, the volume of the gas collected, recorded, and the temperature and air pressure are also being recorded because it carries a valuable information and, with respect to the mathematical formula. Now, the percentage of nitrogen easily we can calculate with the help of this mathematical relationship. 28, that is the molecular weight of nitrogen into volume of the nitrogen at normal temperature and pressure multiplied by 100 divided by 22,400, a magical number, multiplied by the weight of organic compound. Now, at the outset, let us have a discussion about how we can determine the sulfur. Now, because sulfur among all is extremely non-eco-friendly element under the ultimate analysis. So, for this we require a bomb calorimeter. So, the unknown quantity of coal is burned in the bomb calorimeter. Whatever residue is remaining in the bomb calorimeter is supposed to treat it with dilute HCl. The extract is treated with barium chloride solution to precipitate the sulfate as barium sulfate. Now, whatever precipitate is generated in due course of time is filtered, double washed, dried and weighed, and a percentage of sulfur is computed from the weight of barium sulfate. This is the standard formula through which we can calculate the percentage of sulfur, that is weight of barium sulfate obtained, whatever obtained in due course of time, multiplied by 32 into 100 divided by 233 into weight of coal sample. Some of the sulfides, sulfates etc., they are present in the fuel, and some of them are present in the major quantity and some of them are present in the minor quantity and some of them are very rare. Now, if we see the major component, that is pyrites, they are present in the most of the fuel. Similarly, barite, they are present in the minor quantity, rest other they are in the rare one. Now, under this head, that is a determination of ash and oxygen. So, the ash determination procedure which we have already discussed in the proximate analysis. So, we can calculate the percentage of oxygen, that is equal to 100 minus whatever percentage of hydrogen we calculated, percentage of sulfur, percentage of nitrogen and a percentage of ash. So, by this way we can calculate or we can find out what is the percentage of oxygen in the sample. Now, here you can see that what is the percentage of carbon, hydrogen, oxygen, nitrogen and sulfur in different type of coal samples. Now, this is for the reference, and like peat, it is having the carbon content of 55 to 60%, hydrogen 6 to 6.5%, oxygen 30 to 35%, nitrogen 1.5 to 2 and sulfur 0.6 to 1. Similarly, lignite is having 70 to 73%. So, more the carbon, then better will be the calorific value. Similarly, anthracite and bituminous coal, they are having the highest percentage of carbon, like anthracite 93% and 4% hydrogen and approximately 3% oxygen. So, it is the purest form you can say of coal. Similarly, bituminous 80% carbon content, hydrogen 6% and 15% oxygen. So, this is the thing, and that is why you find that bituminous and anthracite coal, they are having the higher cost compared to the peat and lignite. Now, let us have a brief discussion about the total carbon and the fixed carbon. Some of the carbon present in the volatile matter is not included in the fixed carbon. So, therefore, we need to find out, and the total carbon is equal to the fixed carbon plus carbon in volatile matter. So, higher the total carbon content, higher the fuel calorific value, and higher the hydrogen content, higher the calorific value in the gaseous products. So, this is by this way we can find out the total carbon. And let us have a brief discussion about the calorific value. This is determined using the Bohm calorimeter, which we have already discussed using the Dulong equation. So, the gross calorific value, that is sometimes referred as GCV, that is GCV is equal to 1 upon 100 into 8080C plus 34,500 H minus O plus N minus 1 upon 8 plus 2220 S with respect to the kilocalorie per kilogram. Now, in this particular chapter, we have discussed about the ultimate analysis and proximate analysis. Now, we have already discussed that what is the importance of these two analyses, because our ultimate aim is to produce or to have a fuel for the heating purpose, whatever we are using for the heating purpose. It should give high calorific value. Apart from this, it should not impart any kind of environmental threats to the environment. It should not impart any kind of pollutant aspect to any system. It should not be a danger to the system in use, like sulfur, it may corrode like other component. So, by this way we can design our system based on the better choice of fuel. Cost, it should be cost efficient, so that ultimate cost of product should not go on the higher side. Although the availability also is very important, we will discuss the availability issue in due course of time in a separate lecture. If you like to have some more study or references, I have enlisted one of the reference for you. You can have a look of these this reference for the future course of study. Thank you very much.